Hey guys, so we're gonna pick up where we left off with stellar evolution, and we're gonna be talking about massive stars. Now, one point I just left out about low mass stars before we get into this is that when you have your star, that the core collapses in on itself and the outer layers get blown off into space, those outer layers create another nebula. You could say a planetary nebula instead of a stellar nebula, because basically what you end up being left with is, instead of a star with nothing around it or with already formed planets, once it explodes you have a small white dwarf in the middle and then all of this material that's been blown off from the rest of the star. And so that, you could say, is a planetary nebula. All of this material out here could go on to form planets that then orbit the white dwarf. Okay, so that's just the last point about low mass stars. You don't really have to worry about that. If you want to, in between red giant and white dwarf, you can just write a little note that the explosion leads to the formation of a planetary nebula. Okay, now with massive stars, they still start the same way. They still start with that gas cloud, but I guess you could just say that the gas cloud is bigger. There's more material, so the star can get way bigger than a low mass star. Okay, so the Sun is a low mass star, but these massive stars are way, way, way bigger. And the way they die is much more grand than low mass stars, than smaller stars like the Sun. So you start the same way with this cloud of gas and dust that, through its own gravity, collapses to form a new star. Okay, so like the Sun, but way more massive. Okay, so you have a new star, and this star will be huge. Now, it might have planets, it might not have planets. It could be very hot, like you can have some larger yellow and white, and I guess maybe some red stars. The red giant stars burn through their energy really quickly and die really quickly. But there are also stars out there called blue supergiants and blue hypergiants, which are really, really hot and insanely huge. If you've ever seen those YouTube videos that compare kind of the size of planets to the Sun, and then compare the Sun to other stars, blue hypergiants go a really long way down that line. They're absolutely gigantic. But basically you have this giant cloud of gas and dust that collapses into a star, but instead of a low mass star, of course, it is now a massive star. Okay, so we went from that cloud of gas and dust that's now collapsed into a brand new star. Now this star, over the course of its life, it'll do the same fusion process that we talked about with low mass stars. It'll convert hydrogen into helium, release some energy, and it'll do that, billions and billions of times. Once it starts to run low, it'll begin fusing helium into heavier elements, all the way up until it gets to iron. And then it runs into the same problem, actually. It runs into the same problem as low mass stars. It can't fuse the iron into anything heavier. Now, here's where it gets interesting. When it gets, as it gets older, it will grow into, an even bigger star. Once again, still like low mass stars, except instead of red giants, these are called red supergiants. So they're way bigger than what we were talking about before, which is natural. If the original star is bigger, then its red giant older version should also be considerably bigger, and so we call them red supergiants. Alright, now these red supergiants, when they reach the end of their lives, basically what happens is the core once again collapses. It can't hold the weight of the star. The output of energy, because of this lack of ability to fuse, it causes the star to collapse. And so basically you have your star here, and the outer layers of the star begin to collapse, but the core is under immense pressure. So it's really the core collapses inwards into a tiny, tiny, tiny space, and it goes so violently that when it collides, when it compresses into that tiny space, some of it, like the energy, rebounds back outwards and blows the other layers of the star off into space. So basically the core of the star collapses, just like with low mass stars, and it blows off the outer layers, just like with low mass stars, except the explosion is way bigger and way brighter. So with low mass stars, that explosion can lead to a planetary nebula where maybe some old planets survived, and maybe some new planets can form. With this basically wipes out the whole planetary system. So when you see those big nebulas that span 3 or 4 light years in space, they probably came from something like this. And so instead of going from a red giant or a red supergiant to a white dwarf with just a planetary nebula in the middle, they result in what is called a supernova, which is a word that all of you have heard before. So basically a supernova is a huge explosion. It's one of the most violent explosions in the universe, and basically it's the death of a very massive star. So the core collapses and it blows off the outer layers deep into space, and actually when that core of the star collapses, it actually churns out all of the elements that you see in the periodic table. So basically, at the beginning of the universe was full of hydrogen and maybe a little bit of helium and some, different isotopes of those elements. You might have had deuterium, which is just another form of hydrogen. But once these kinds of stars began to die, as that core collapsed, they cooked up elements like gold, mercury, uranium, Einsteinium. All of these kinds of elements would have been churned up in those kinds of supernova explosions. And then they were spewed out into the universe because the star explodes. So all of the material that's inside gets spewed out into space. But here's the thing, that core of that star gets compressed into a really small space. And we call that leftover thing a stellar remnant. Now, what are stellar remnants? They're basically the leftover dead corpses of stars. Okay? So basically, there are a few types of stellar remnants. I'm going to get rid of these pictures. You can finish writing down that chart of, or that flow chart of what happens to massive stars. It ends with a stellar remnant, but then we're going to talk about the different types of stellar remnants. Alright, so one of them we've actually already talked about, and it is the white dwarf from low mass stars. It's basically the leftover corpse of a dead star. But there are 2 more types of stellar remnants that are much more extreme objects, and I'm sure you've heard of at least one, but you may have heard of both. The first one is called a neutron star. And the second one is called a black hole. Okay? So this is what we're working with. We've got neutron stars and black holes. Now I know all of you have heard of black holes because we all watched that announcement last month. But neutron stars are kind of funny. They're similar to white dwarfs in terms of their size. They're Earth-sized, whereas black holes, for massive stars that aren't humongous, they'll be, even smaller than Earth, maybe. Like maybe Mars-sized or city-sized. Neutron stars, basically the way they work is they're basically like the nucleus of an atom, in the sense that atoms themselves are mostly empty space, but the nucleus of an atom is very tightly packed. And so basically what happens for forming a neutron star is if you have an atom, you've got your nucleus in the middle and your electrons on the outside, right? Atoms don't look like that, but something like this, all right? So you've got your nucleus in the middle, tightly packed, and you've got your electrons on the outside. Now, if the star is collapsing so violently and under such great pressure that there's no space left over, what happens is these electrons get forced into the center by other atoms that are nearby, that are just getting too close. These electrons get forced into the middle, they fuse with protons, and basically become neutrons. If you take a proton, which has about the same mass as a neutron, and you just add the charge of an electron to it, well, a proton has a positive charge, a neutron has a negative, or an electron has a negative charge, they cancel out, and you basically have something that's got the charge of a neutron and the mass of a neutron, so it's a neutron. And so you get these nuclei all packed together in the middle, and there's no protons there, and there's no electrons there. It's all just a sea of neutrons really tightly packed together. And so basically the entire neutron star, if this is Earth, you might have a neutron star that's this big, and it's basically a giant atomic nucleus full of neutrons with no empty space. So they're incredibly dense, because if you have something that's Earth-sized, you'd expect it to have Earth's mass. But if you have a neutron star that's Earth-sized, then it would have a mass that's probably a few billion times greater than the Sun, or at least several thousand times greater than the Sun, which is a lot to pack into that kind of space. And the reason you can pack all of that into that kind of space is that this space between atoms doesn't exist. It's all so dense. The thing with neutron stars, though, is that they can still emit light, they can still emit radio pulses, and those are different types of objects that you can observe. Neutron stars are known for having very specific radio pulses that they emit called pulsars. It's basically a radio signal that you can receive from a rotating neutron star. Now, black holes are even more extreme. Basically, with a black hole, you crush all the matter of a star down to a space so small that the speed you would need to travel at. So let's say you had your star, and then it gets compressed into a really tiny space, but that tiny space contains the mass of this whole thing. All right, that whole mass of the sun, or of that star, is contained in this little thing that we call a singularity. All right, that's the thing at the center of a black hole. Now, for Earth, if you were to compress the mass of Earth down so small that you were to get a black hole, it would have to be about the size of a peanut, if that gives you an example of what kind of compression you're dealing with. If you could compress the whole Earth down to the size of a peanut, you'd have a black hole. Now, the thing with regular Earth, the Earth that we know, is that if you want to escape Earth, all you need to do is travel that way at the right speed, at a fast enough speed. And at the surface of Earth, it's not the gravitational pull is strong enough to keep us attached to the surface, but if you can travel at about 11 kilometers per second that way up, then you will leave Earth's gravitational pull. You will be going fast enough that you can go up and not come back down. If you're going any slower than that, you'll go up, you might go all the way up so that you can see Earth from space, but then you'll fall back down. So 11 kilometers per second is the speed you need to travel at to get away from Earth's gravitational pull, and we call this escape velocity. Now, with black holes, the singularity of a black hole, it has such a strong gravitational pull because it's got the whole mass of the star, but with a star, it's got the whole mass of the star is pulling on you, but it's so spread out that the gravitational pull at the surface of the star is not super extreme. But with this, it's such a small space with such a big mass that the gravitational pull is really extreme. And basically what you get is that the escape velocity, the speed you need to travel at to leave the black hole's gravitational pull, in other words, to jump up and not fall back down, that speed that you need to travel at is faster than the speed of light. And so basically what that means is even if you have light trying to escape by going directly away from the black hole, it's traveling at the speed of light, not faster than the speed of light. So it goes up and it gets pulled back down by the black hole. And that's why around the singularity you have this region, this dark region, from which no information can leave the black hole. And the boundary of that region is called the event horizon. That's a term that maybe will be familiar to you guys. We were talking about the Event Horizon Telescope. We're the ones who were trying to take a picture of the event horizon of a black hole. So that's basically what you're looking at. If you are on the outside of a black hole, everything inside the event horizon just looks black because none of that light, none of that sound, none of that information is getting out to you. So it's just this big black sphere, and that sphere, what that you're seeing, is the event horizon of a black hole. Now once you get far enough away from a black hole, the escape velocity drops to the speed of light or below, and then that's the stuff that you can see. So the event horizon shows you the limit between the escape velocity where you can get away from the black hole and the escape velocity that's impossible to reach, that you cannot get away from the black hole. Alright, so we'll talk more about black holes later on. I won't test you very extensively on it because the math and stuff gets advanced and the concepts can get advanced as well. But I wanted you guys to see what black holes are, why are they black, because light can't escape, but why can't light escape? So I was hoping to give you guys a better understanding of that, and hopefully after this you have a more clear understanding of what black holes are and how they're kind of similar to neutron stars. They're kind of more extreme versions of neutron stars, and both of them are products of the death of a massive star. Alright, I know that was probably a lot to take in if this was your first time hearing about this kind of thing, so if you have any questions or concerns, leave a comment, send me an email. Otherwise, I will see you guys in the next video. Hope you enjoyed it.